Bismillahirrahmanirrahim. Today's video is from Signals and Systems, chapter number 2. And here we'll be discussing block diagram representation of first order system described by differential and difference equation. And this is on the request of a student. So let's see. First of all, we'll do the difference equation, presentation of difference equation. And if you recall, the first order differential equation is written like dy dt plus some y and then x. And the first order difference equation is written as yn is equal to ayn minus 1. So there is a delay here. Delay and then bx. So in this case, we'll now follow this formula shown here. And from here, we can write yn equal to, we move this to the right hand side. And now to implement this equation, we'll need an adder sign here. We'll also need a multiplier because we are multiplying by a. And we also need a unit delay circuit. So delay, so this is a unit delay. So we'll need these three things. And so first of all, let's start with the input x. Xn multiplied by b, so it will be bxn. We put the adding sign here. The other input is coming from down or the feedback side, and it has to be minus a yn minus 1, this term. And now this is equal to yn, so we draw this line yn. But then we have to put the feedback loop as well. So to get this one, we have to use a delay circuit. And then we have to use a multiplier circuit. So the output of the delay is yn minus 1. And then we have to multiply it by minus a. It will be minus a yn minus 1. So this is the complete block diagram for the given equation. We will follow same technique to solve these two, question number 238, part A and part B. Now part A, first of all, as we did the last slide, we'll follow exactly same xn multiplied by half. Then we put the adder sign. We put the feedback line, this one, 13yn minus 1. Then we connect and go to the while. And then we also get the feedback from here. The feedback line, the delay line, yn minus 1. And then we need to multiply by 1 over 3. So multiply by 1 over 3. So this is the block diagram for given equation. Coming on to equation B, the only difference is that we have a delay with the input as well. Here, xn minus 1. So first of all, again this one. So the delay, x input has been delayed now, xn minus 1. Then we add adding sign. Then we get the feedback, and connect y. And now the delay loop, this one, yn minus 1, and multiplier of 1 over 3, so multiplier of 1 over 3. So this is the block diagram for the second part. Now we go to the differential equation, first order differential equation. This is the first order differential equation. From here, we'll try to write yt. And to write yt, this yt, we divide by a. So first of all, we keep it on the left hand side This one goes to the right hand side and then divide by A. So we get this equation. I hope you can do this. And here also we'll need the three elements, adder and multiplier, and now this D will be for differentiator, in this case dy dxt dt. So if you follow the technique that we discussed earlier, we first of all take this, that was xt multiplied by b over a, go to the addition sign, then we do this feedback. This is the feedback, connect y, and then the differentiation d, this gives us dy dt, and then minus 1 over a multiplier, so we get the feedback part. So this is the block diagram. We'll follow the same technique. Okay. While figure 230, this is figure 230, is a valid representation for the causal system. I hope you remember what is causal system. A causal system depends on the present value and the past, not the future. The causal system described by equation this one. It is not representation that most frequently used. And the reason for not using this most frequently is that the differentiators are both difficult to implement and extremely sensitive to error and noise. So instead of differentiator, we'll try to convert it in a form so that we can use integrator circuit. And for that, we rewrite this equation. And from here, integrating both sides. So if we integrate, we get yt, and we integrate the right hand side. The limit is from minus infinity to t. And I hope you remember that for integration, because we are integrating up to a variable t, then this variable t will have to be changed to tau. We change this variable to tau d tau. Also, we are assuming that the value at y minus infinity is 0. That is, there is nothing stored previously than infinity. And so this can be implemented, or any integrator can be implemented as xt, the integrator circuit. So the output will be from minus infinity to t x tau d tau. So we'll follow this here. So in this case also, now we have the xt input multiplied by b, so b xt, and then plus minus a y tau. So minus a y tau is the feedback. Both of these are fed to the integrator, and the output of the integrator is yt. And to get the negative multiplication by minus a, this one minus a, so we take the feedback loop, and y tau minus multiplied by minus a, it will be minus a y tau. So this is the circuit that will follow. Now the two examples, two part of example question 2.39. Let's do the first part. This is the question. So we write it in the form of differential. First, this one we bring here, and then this move to the right. And then we take the integration, the rewriting. We move this to the right hand side also. So like multiply by 2 both sides. So this one vanishes from the left. Integrating and changing the variable from t to tau. Yt will be integral minus 8 tau, and then x, minus infinity to t, x 8 tau minus to y tau d tau. So this is what we should be integrating, this part. And as we discussed in the previous slide, so the input here is x multiplied by 8, and the feedback is minus 2yt, and then we integrate this, we integrating to get yt. Now the feedback loop is we're just multiplying the output by, yt by minus 2, output yt by minus 2 to get the feedback loop. And the solution manual, okay, at this point is the after the integral, we are actually getting this whole thing here. The solution manual has followed a different approach, which I did not agree, and therefore I took help of ChatGPT. What they have done is actually they have broken this into two parts and then have used two integrators. So one integrator for the first one and the other integrator for the y, and then adding. Apparently this looks okay, but I had my doubt, because let's say the moment you start, what you get here is integral of 8x and nothing, no feedback as yet. So integral of 8x is again getting integral from here integrated. So this did not sound good to me. So I took help of ChatGPT and I asked this question. But what ChatGPT is saying, that since yt, this yt is like this, therefore if we differentiate this, then we get this term from here. And this dyt is the y dash t is equal to minus 2yt and plus xt. So what he's saying, that the integrator implements yt is equal to integral of y dash t. So yt should be the integral of this thing. The input to the integrator must therefore be this whole thing. So the input to the integrator, as we have, must be this thing, not the two different integrators. Okay, the second part is exactly similar. Moving and then writing in terms of integration, giving the xt and minus 3y tau, summation sign, then integral, and then feedback with minus 3, minus 3 feedback, and this should be the answer. I hope you have been able to follow this. Please let me know through your feedback. Thank you. Okay, just for your knowledge, this is what the solution manual has given for this one.